Hey everybody, welcome back. Today we're going to be discussing the derivative and the power rule. Let's begin. Suppose I have a function y equals x to the power of r, where r is real, that is, such as -1, 0, 1, 2, pi, etc. The power rule tells us that the derivative of y, dy by dx, is going to be r multiplied by x to the power of r minus 1. That is, we bring down the power and then we subtract the power by 1. Let us look at an example. Suppose y is equal to x squared. Then dy by dx is going to be, we bring down the power 2 multiplied by x and we subtract 1 from the power, so we get 1, or 2x. So y, which is equal to x squared, is a parabola that opens up and begins at the origin. And y equals 2x is just a straight line with slope equals 2 and no intercept. Let us graph that and take a look at what it looks like. Here's our parabola that opens up, y equals x squared. And here's our straight line, dy by dx equals 2x. Let's consider another example now. Suppose I had the function y equals the square root of x. We can rewrite that as x to the power of 1/2. Then by the power rule, we bring the 1/2 in front, so we have 1/2 x, and then we subtract 1 from the power. So we'll have 1/2 x, 1/2 minus 1 is minus 1/2, or we can rewrite this as 1/2 over the square root of x. Let us graph that and take a look at what it looks like. We have our exponential function y equals square root of x here, and then we have our derivative dy by dx, which is 1 over 2 root x here. In the first case, x to the power of 1/2, we notice that this can be 0, but in the second part, in the derivative, it cannot be 0. Cannot be equal to 0, because if we had 0 on the bottom, we'd have 1 over 0, and that would be infinity. So you can see as it approaches 0, it tends to infinity up here. And then y equals square root of x, our original function, is always positive, always greater than 0, because you can't take the square root of a negative number. Let us look at another example. Suppose I had y equals 30 x cubed. Then dy by dx will be 30 multiplied by, we bring the 3 down, then we have x, and then we subtract 1 from the power, so 3 minus 1 would become 2, or 90x squared. In other words, the original constant appears in our derivative down here, so it has no effect on the derivative. And the rule is that if I have a constant multiplied by x to the power of r, and I take the derivative dy by dx, that is the same as saying c multiplied by d dx of x of r, which is c multiplied by rx r minus 1. So let us graph the function and its derivative and take a look at what it looks like. Now we should recognize this is a cubic, so this is our original function, 30x cubed. That is the purple line. And the red parabola is our derivative, which is 90x squared. The parabola is opening up, that is, y is never less than 0 since it's 90x squared. And then the cubic could take on both functions f and g, and they're both differentiable. And I wanted to find their derivative. Then the derivative of f plus g is the derivative of the individual functions df dx plus dg dx. Let us consider an example. Suppose I had y equals 4x cubed plus 3 square root of x. Then dy by dx is, we just take the derivative of each of these. So we'll have 4 times 3x, and then 3 minus 1 is 2, plus here, this is 3x to the 1/2. So we'll have 3 multiplied by 1/2, and then x to the minus 1/2, which gives us 12x squared plus 3 over 2 square root of x. Let us look at the graph of this. Our original function, y equals 4x cubed plus 3 square root of x, is this purple line, while the red line, or the red curve, is our derivative, dy by dx, which is 12x squared plus 3 all over 2 root x. Now we notice that our derivative here, x cannot be 0, but as x tends to 0, it blows up. And our original function here, y must be greater than or equal to 0, because x can't be less than 0 because of the square root. And you can see here that y is always greater than or equal to 0. Let us consider one final example. Suppose I had a function s of t, which is 17 minus 4t squared plus 8t cubed minus 9 square root of t. And I wanted to find ds dt. Well, we take the derivative of each of these terms. So the derivative of a constant will become 0. Then we move on to this one. We have minus 4. Derivative of t squared is, we bring down the 2 to t. We reduce the power by 1, plus 8. We bring down the 3 times 3t. We reduce the power by 1, that becomes squared, minus 9. And then we remember the derivative of the square root of t is just 2 over square root of t. Continuing, we have ds dt equals minus 8t plus 24t squared minus 9/2 square root of t. Now let us graph the function and its derivative. Take a look. Again, the purple curve represents the function s of t, and the red one is the derivative ds dt. Now we notice when t is 0, then s of 0 is 17, which when t is 0, y is 17. And the red curve here, t can never be 0, or else this would blow up, this term here, and would tend to minus infinity. And you can see that that's exactly what happens. It tends to minus infinity as it tends to 0. To summarize, we looked at 5 different examples. On the left-hand side are all the functions, original functions, in blue, and on the right-hand side in red are their derivatives. Take a look, review, practice, and we'll see you next time. Have a great day. Please click like, subscribe, and comment below. Ciao, bye.